Okay, so good evening, everyone. This is the 12th and the last live session for this last live problem solving session for this course, Numerical Methods for Engineers. Uh, one more session will be conducted after this 12th session on 19th of October, where I'll take a 1 hour session and let you know how to implement this numerical techniques, solution of the numerical differential equations, and all the techniques which we have learned through a programming language like MATLAB. And you can visualize in MATLAB how we can get to the solutions. So let's get started for today. So last class I was stuck in between, and due to power cut I could not complete the whole thing. So basically, I'll just give a quick recap. We were talking about stability analysis, right? So, so our aim was basically to determine whether a particular algorithm to solve an ordinary differential equation is stable or not. So we learned many methods, right? First was Euler's explicit method. Then we learned many implicit methods. And so Euler's explicit method, it is generally for lower value of step sizes, it is generally unstable. And these implicit methods are much more stable. So what causes the instability that we need to first address? So the thing is basically there can be two types of instability. One is the spurious solutions, that is solutions which are not true at all. That false solutions are creeps in between the true solution. Second, we have the numerical error. This numerical error is unavoidable, and that is inherent to any numerical technique, and that with the iteration that numerical error keeps on accumulating. So these are the two types of ways in which a solution can be unstable. So now we want to find out general stability criteria for a particular ODE, and I will show you how the spurious or false roots exists, and then by graph we'll try to understand why, how the stability and what all parameters are involved in the stability of that particular differential equation. So here generally we consider a general ODE solver algorithm where this yn plus 1, it depends on the other values of y, like yn minus 1, and also the derivative of that particular terms. So here alpha naught, alpha 1, alpha 2, and alpha k, these are the different coefficients, right? These are the different coefficients. And here we have just written in terms of the weighted average of the terms of the differential equation. Now, this is the this yn plus 1. Let us number this as equation 1. This equation 1, let us apply this to a simple ODE. Just a simple ODE we will take, which is dy by dt equals to lambda y. Hello, Nasim, are you there?
Yes, yes, I'm here.
Okay. So just I started. So basically,
Okay,
I'll
okay.
continue from the part where I left in the last class. This
Okay.
yn plus 1, it is a general ODE solver algorithm. The equation, general equation for an solving an ODE. So let us apply this equation to a simple ODE like dy by dt equals to lambda y, right? And generally for most of the algorithms which we have learned, this alpha naught coefficient, that is a coefficient of yn plus 1, is basically 0 in most of the cases if you see the Euler's technique, the Hume's method, or the RK4 method. So if we substitute alpha naught equals to 0, we can rewrite this equation as yn plus 1 is equal to alpha 1 yn plus alpha 2 yn minus 1 plus like that up to k terms alpha k yn minus k plus 1. Then comes the derivative terms, right? So here we had h beta naught yn plus 1 dash. So this yn plus 1 dash, that can be represented by lambda yn plus 1 from this differential equation. So this dy by dt equal to lambda y, what does it mean? It is basically y dash equal to lambda y, right? So here yn plus 1 dash will be lambda yn plus 1. Like this we will continue and we'll get another k terms here. Plus beta k lambda yn minus k plus 1. This is equals to yn plus 1, right? So now if we just club the terms together and little bit simplification if we do, we will get like this. H beta naught lambda One second. Now, this yn plus 1 on the left side, if we bring to the right hand side, everything we are bringing to the right hand side. Yn plus 1 plus alpha 1 plus h lambda beta 1 into yn. Like this, it will continue. Last term will be alpha k plus h lambda beta k yn minus k plus 1 equals to 0. So this equation, if you look into, let us number this equation as equation 2. This is basically a difference equation. What is a difference equation? Difference equation is a discrete rather than a differential equation. The differential equation basically involves the continuous derivative, right? Whereas the difference equation involves the discrete value of the function at discrete intervals. So this yn plus 1, yn minus 1, all these are the values of the function at discrete time interval, discrete values of the independent variable. So this is basically a linear difference equation. Equation 2 is basically a linear difference now we have the differential equation dy by dt equals to lambda y, right? And the initial condition, let us assume y of 0 is equal to some constant c. Okay. So now if we solve this equation analytically, what we will get? We will get dy equals dy by y equals to lambda dt, right? We integrate it on both sides. Ln y equals to lambda t plus c. Now, if we substitute this y of 0 equals to c, how much we will get? Let us assume this is c1. So, ln c1 equal to c will be equal to ln c1, right? So now, if we substitute here, it will be ln y equals to lambda t plus ln c. So ln y by c1 will be equals to lambda t. Y will be equal to c1 e to the power lambda t, right? So this is the solution of this differential equation if we solve it analytically. So now let us assume this e to the power lambda t as a variable mu, some mu. Okay. So what will be y of 1? Y of 1 will be c1 into mu. What will be y of 2? Y of 2 will be c1 into mu square. Like this, it will continue and we will get y n minus k plus 1 equal to c1 mu to the power n minus k plus 1 and we'll get y n plus 1 equal to c1 mu to the power n plus 1. So if we just manipulate this thing, this yn plus 1 is equal to c1 mu to the power n plus 1, right? So if we just write like this, c1 mu to the power k n minus k plus 1. In this format, we are trying to write. Okay. So now these values of y1, y2, yn plus 1 all, we will substitute in the previous equation. So what was my previous equation? It was basically h beta naught lambda minus 1 to mu k. So lambda is y of 1 is this constant will get, okay, I'll do it for you and just write what was the equation previously. So this equation I'm telling h beta naught lambda minus 1, this one. So the equation was h beta naught lambda minus 1 yn plus 1 alpha 1 plus h beta 1 lambda yn right? Like this. we have up to k terms, right? That is alpha k plus h beta k lambda y n minus k plus 1 equal to 0. So now in place of this yn plus 1, we will substitute this c1 mu power k mu power n minus k plus 1. So this c1, just have a look, try to understand. So h beta naught lambda minus 1 c1 mu to the power k n minus k plus 1. Alpha 1 plus h beta 1 lambda. What will be yn from here? If you just keep this here, yn will be c1 mu power k, right? Sorry, c1 mu power n. If we just will be mu power k, mu power n minus k. Correct? Just a second. One second. You of 1 we can write. Just a second. Okay. Okay. Okay, understood. Just replace yn by c1 mu power k. So this is that we are taking this c1 and mu power n minus k plus 1. This you have to keep in all the terms. So if we just replace this one here, we write it c1 mu to the power n minus k plus 1. What does it? So remaining is k minus 1. So that is what. So here we will write c1 mu power n minus k plus 1 multiplied by mu power k minus 1. Like this we will continue. We'll have alpha k plus h lambda beta k. And what was the last term here? Yn power yn minus k plus 1. So it will be y of n minus k plus 1. Okay. So this is this one, right? C1 mu to the power n minus k plus 1. So this is C1 mu to the power n minus k plus 1. Just means after I complete the lecture, just go through it once. If you have any problem, you can ask me. So here you can see this in all the terms C1 and mu to the power n minus k plus 1 is common. Okay. So we'll cancel it from all sides, both sides. So what we will get here, h beta naught lambda minus 1 to mu k, mu to the power k plus alpha 1 plus h lambda beta 1 mu to the power k minus 1. Like this, last term, everything will get cancelled. H lambda beta k equals to 0. Is this clear to you? How did this equation come?
Yeah, clear. That C1 mu to the power n minus k plus 1, it's a constant term.
Yeah, it is common.
Okay.
So from this, you can see this is a equation, the solution of this equation will be given by, if you just solve this equation for your solution will have k roots. I'm not going how it is, what are the solutions, but just remember this one, it is required for the derivation. So the roots are mu1, mu2 up to mu k. Okay. It will have k roots which are given by mu1, mu2 and mu k. Therefore, what will be the solution? This yn plus 1 will be given by c1 mu to the power n plus 1, c2 mu2 to the power n plus 1, ck mu k to the power n plus 1. So this is the solution of this yn plus 1, what we get from this equation, from the characteristic equation. However, we know that this dy by dt, what was our original differential equation? It was dy by dt equals to lambda y, right? So we know that it has only one exponential terms, whereas here there are multiple exponential terms because mu itself is e power lambda t. So there are multiple exponential terms here. So where is the catch? Now, our ODE initial value problem has only one exponential term, which is given by y equal to y naught e power lambda t. This was our solution. However, from this difference equation, we are getting a different solution, but that is not possible. So this is where we get some false roots or spurious roots. So this equation, but our equation 2 shows several exponential terms. Therefore, these are all spurious or false roots. So that means, if only one term has to stay in the solution of yn plus 1, what will be the condition for that? That means any one particular mu, that is any one particular mu, the magnitude of that should be greater than all other mu's, right? That can be any mu. So in order to have a single solution for this equation 2, I'm again repeating it, that equation 2 has multiple solutions and there are multiple exponential terms here. However, we know that our original ODE, it has only one solution, one exponential term in its solution. So that's why in order for equation 2 to have a single exponential term in its solution, any one particular value of mu, that is either mu1 or mu2 or mu3, any one up to mu k, that should be much greater than the other values of other mu values. Okay, that then only we can ignore the other smaller values of mu and we can take only one term. Is this clear to you?
Yeah, it is clear.
Now, this value of mu is dependent on h, the step size, lambda, and alpha, beta. So this is the conclusion that we are drawing here, that only one value of mu should dominate over all other values of mu. That is either mu1 or mu2 or mu3, any one should be greater than all the other values. Then only this solution will be stable or consistent. We'll see this through one example. Okay.
Hello.
Yeah.
Means it will be given in the question, means which mu value is stable.
No, based on a differential equation, you have to plot that. I'll just show you how to do that.
Okay.
I'll just do and I'll show you.
Okay.
So the question is, obtain the characteristic equation of the following algorithm. And study its stability. So what is the algorithm? The algorithm is given as yn plus 1 equal to yn plus 2h yn dash. Okay. So this is given to you. Now we have to apply this on a particular differential equation, right? So let us apply to dy by dt equals to lambda y. Okay. So what is our equation now? Yn plus 1, yn plus 2h yn dash. So now y1 was c mu, like this up to yn plus 1 was c mu power n plus 1. So here in this equation, we have yn plus 1, right? What will be yn plus 1? It is c mu power n plus 1 c mu power n plus 1, yn equals to c mu power n, and yn dash, and yn minus 1, sorry. Yn minus 1 is not required, still we'll write it. So now let us substitute in this equation. So yn plus 1 is c mu power n plus 1, yn is c mu power n. What is yn dash? From this differential equation we know, right? Yn dash is lambda yn. Lambda, and again yn is c mu power n. So from all these terms, if we cancel mu power n, what we will get? C mu power n is common in all the terms, right? So here we will get, 1 second. Okay, so this equation I have not written correctly. Is yn minus 1. So yn plus 1 is yn minus 1 plus 2h yn dash. So this will be yn minus 1. This will be mu n minus 1. So mu n minus 1, we are dividing both sides by mu n minus 1. Okay. So this will be mu square. This will be 1. This will be 2h lambda. Right here. Dividing both sides by c mu to the power n. So we have this equation, mu square minus 2h lambda mu plus 1 equals to 0. So this is a quadratic equation, right? We can solve that. Lambda plus 0. So two roots will come. These two roots are, this is one root. Other root is h lambda minus root 1 plus h square lambda. So these are the two roots, right? So now, what is the solution? We have to understand now. Is it clear to you, right? What I'm doing?
Yeah, clear.
Okay. So yn plus 1 will be c mu to the power n, mu 1 to the power n plus 1, c mu 2, so c1. So here also you can see there are two exponential terms, right? C1 and C1 mu 1 to the power n plus 1 and C2 mu 2 to the power n plus 1. However, true solution is y equal to c e power lambda t, which has only one exponential term. That means either mu1 or mu2 is a false root, right? That is, as one root is real and the other root is spurious or false. So now, using graphical method, we'll try to understand what will be the condition for mu1 to be greater than mu2 or mu2 to be greater than mu1. Okay. Now, the true value of mu, either mu1 or mu2, is greater than the other value of mu, much greater, then this algorithm can be stable. Okay. So now, okay. Now, how to understand whether mu1 is greater or mu2 is greater, right? Remember what is mu1 and mu2. These are the expressions for mu1 and mu2. Here, h lambda plus 1 under root 1 plus h square lambda square. Other is h lambda minus, right? So if you plot it with respect to h lambda, this value of mu, so this one is mod of mu1, this one is mod of mu. If you just plot it in MATLAB, you will be able to see how the plot of mu1 and mu2 looks. And see this one here, what was the true solution? It is y equal to c e power lambda t, right? Which is, what is c e power lambda t? If we plot it, how will it look like? It will be an exponentially increasing function, right? So here, mu1 or mu2, which one is an exponentially increasing function? This mu1 is an exponentially increasing function, whereas mu2 is an exponentially decreasing function, right? Hence, our true solution is mu1, not mu2. Since true solution is exponentially increasing, mu1 is the true solution. Okay. And okay. So mu1 is the true solution, and this method, this algorithm will be stable only when mu1 is greater than mu2. Now, when is mu1 greater than mu2? From this graph, you can understand mu1 is greater than mu2 only when h lambda is greater than 0, right? Because in this right half of this red y-axis, that in that part only mu1 is greater than mu2. That is mod mu1 is greater than mod of mu2. This is possible only when h lambda is greater than 0. Now, h is always greater than 0 because it is the step size, right? That is, these are the conditions for stability. Lambda must be greater than 0. Then only your solution will be stable. Is the concept clear?
Yes, it is clear. So means when lambda is greater than 0, then we will get the means
We'll get a stable solution.
stable solution, and then the means function will be increasing in nature.
Yeah.
Okay.
Clear, right?
Yeah, clear.
2 minutes, I'll come back. Okay, so this was all about the stability of this ordinary differential equations. So this is all about initial value problems of ordinary differential equations. So now we will start the last topic of this lecture, which is boundary value problems. Okay, so this differential equations are of two classes here. One is the initial value problems, in which one of the initial values will be given to you, and based on that you have to solve the differential equation. So apart from that, there is one more thing which is called boundary value problems, in which the value of one of the value of the dependent variable at two different values of the independent variable will be given to you. Okay. So I'll just show you how it is done. So there are different algorithms for solving these boundary value problems. And before we go into the algorithm, some of the theory we have to look into. So we'll do that. Okay. So our topic today is ODE with boundary value problems. So what are these boundary value problems? So here the value of the dependent variable. So here y is our dependent variable and x is the independent variable, right? So value of the dependent variable is specified at two different values of the independent variable. Okay, so now we'll see here one example. First, we'll see what I am meaning by the boundary. You will appreciate that example first. Then we'll see how to solve it. So I'll give an example from the domain of electrical engineering. So in your class 12, every one of you, all of you have learned this capacitor, right? What is a capacitor? Basically, there will be two plates, two metal plates. So you are able to see the screen, right?
Yeah, it is visible.
So basically, what is a capacitor? Basically, a parallel plate capacitor we tell. So basically, there will be two metal plates, and one plate will be grounded, that is, it will be connected to zero potential, and another plate that will be connected to your supply. And in between the two plates, there will be a kind of dielectric. So that is you don't need to understand what is dielectric and all those things. Just remember that there are two plates. These are the two boundaries. One boundary condition is specified, that one of the plates is connected to ground, that is its potential is zero. Another plate that is connected to a voltage V. So that condition is also specified to you. Okay. Then you have to find out what is the potential at the interior points, that is between the two boundaries. What is the value of my function? So basically the potential distribution within a parallel plate capacitor, the equation for that is basically given by d square v d2 v by dx square is equal to 0. This is called as Laplace's equation. So here you can understand that x is my independent variable. X is my independent variable and y and v is my dependent variable. Okay, v is my dependent variable, x is my independent variable. So now suppose I'll draw my coordinate system. We'll make it here is the x equal to 0, and here is, suppose the length of this parallel plate is L. So this is x equal to L. So in this point we will divide the domain into, say, n number of points. Equispaced points we have to do. This is x equal to 0 plus h. This is x equal to 2h, x equal to 3h, x equal to 4h, and this is my boundary, x equal to 5h, right? So what is given to you? V of x equal to 0 is given as 0, and v at x equal to h, x equal to 5h or x equal to L is given to you as, this is say v1. These two conditions are given to you, and based on these two conditions and the differential equation which is given to you, you have to basically find out what is the potential distribution. That is the basically potential distribution here means at this points only, this discrete points 2, 3, 4. These interior points, what is the potential that you have to find out. Is the concept clear what we are going to do here?
Yeah, it is clear. It's one dimensional Laplace equation, I think.
Yeah, this is one dimension only we will talk about here. We will not go into
Oh,
two dimension.
okay.
Okay. So now with this knowledge, now we will move to the what are the different numerical techniques to solve a boundary value problem. What are the numerical techniques to solve a boundary value problem? So first is finite difference method or FDM. FDM. One more technique is available, which is known as orthogonal collocation technique. So in this particular course, we'll be only studying about finite difference method. Okay, so finite difference method, and the second is orthogonal collocation technique. Now we need to understand what are the boundary conditions. So here, did you understand what was the boundary condition? One boundary condition was v of 0 is equal to 0 and v of 5h or v of L is equal to v1. These were the two boundary conditions. So directly here, the value of the independent variable was specified to you. It can be some other way also. So we will see what are the different boundary conditions. What are the boundary conditions? First is known as Dirichlet boundary condition. So here the value of the dependent variable is directly specified, like in the previous problem what we saw. So the value of the dependent variable is specified. that is v at x equal to say 0 is given as 0 and v at x equal to L is given as some other value k. So this is known as Dirichlet boundary condition. Second type of boundary condition is Newman boundary condition. So what is Newman boundary condition? Here the value of the dependent variable will not be specified. However, value of the derivative of the dependent variable will be specified. Derivative of the dependent variable is specified. Like it will be given dy by dx at x equal to L is equal to k. So this type of solutions will be given to you. Just a second. So, and third kind of boundary condition is known as Robin boundary condition, Robbins rather, or also known as mixed boundary condition. So here both the a linear combination of the value of the variable as well as the derivative of the dependent variable will be specified. Like it will be given to you a into y at x equals to L plus b into dy by dx at x equals to L is given by some constant c. So like this it will be specified to you. So there are three types of boundary condition. Is it clear the different boundary conditions?
Yeah, it is clear.
Just take some time. If you have any questions, you can tell me up till this.
No, you can proceed. I'm clear.
Okay.
In Dirichlet's condition means initial and final values are given.
Yeah, initial and final values of the dependent variable is given to you.
Okay. Okay.
Fine. So now we will see what is the finite difference technique. So let us consider a second order ODE boundary value problem. Okay. So it will be basically a function of the second order derivative, first order derivative, and the function and the dependent variable. And also the it can be independent variable also can be there. So this is the general form of a second order ODE. And what will be the boundary conditions which can be given to you? One will be I'm considering both the derivative as well as the value of the function. That is mixed boundary condition I'm considering here. Okay. This is at one point and this dy by dx and this two boundary conditions are given. So now what will be our basic aim here? So these are differential equations. We will be converting these differential equations to simple algebraic equation to algebraic equations. Okay, so how can we get ODE from any kind of differential equation? How can we convert it to an set of algebraic equation based on whatever we have studied? Can you recall anything, Nasim? Any idea?
Means why converting the ODE by
Yeah,
integrating.
like in the ODE, what will be the terms? Like dy by dx will be there, d2y by dx2 will be there. So I'm telling those terms, can you convert it into some algebraic equations?
Yeah, by integrating the whole equation.
No, no, no. How can you integrate a nonlinear differential equation? You cannot integrate. So based on any numerical technique, you can find. We studied in numerical differentiation, right? How we can represent dy by dx, then d2y by dx2 using the forward difference, backward difference, all these formulas we looked into, right?
Okay, okay, that one.
This forward difference, backward difference, these are nothing but we are converting this differential equation, differential terms to algebraic terms. Okay.
Okay, okay.
So before we go into that, we have to first understand how to discretize. So discretization is the crux of any numerical method. So what is discretization? We will be dividing the domain into n equispaced points. So if we have n points, that is n, like if we have a line like this, and if we have n equispaced intervals, rather not points, intervals. So we will have n plus 1 points always. See here, there are how many intervals? 1, 2, 3, 4, 5, 6. However, points are 1, 2, 3, 4, 5, 6, 7. So basically, if we have n equispaced intervals, we'll be having n plus 1 equispaced grid points. Okay, where this the gap between the successive points, that is xi plus 1 minus xi, will be given by delta x. That is the discretization unit. Okay. So that this xi plus 1, that can be represented by I minus 1 into delta x. What is delta x? We can write as x n plus 1, that is the last point, minus first point, divided by number of intervals. Is this clear?
Can you repeat it once again?
Yeah, like xi plus 1 is, say this point is, I am telling xi. Okay,
Okay,
this point is xi plus 1. So the gap between this xi plus 1 and xi is delta x. Okay, xi plus 1 minus xi is delta x. So now, how did this second equation come? Suppose we have like this, and we have, say, just take 3 points. Okay, this is x1, x2, x3, x4, x5. This gap is delta x, delta x, delta x, delta x. So if we take this as the reference, x1 says 0, 0, then what will be x4? x4 is 3 delta x, right? So we can write generally this xi, sorry, this is xi, not xi plus 1. So xi will be given by I minus 1 into delta x. Is this clear? How did this equation come?
okay, okay. Understood.
So this
Got it.
delta, yeah, yes.
Got it. Got it.
Okay. So this I minus 1 delta x, right? So this delta x, we can also represent it xn plus 1, that is the last point, minus the first point, divided by number of intervals, right? So that is very obvious. Now we will see the algebraic expressions for this integrals. So now we have to develop algebraic expression or dy by dx, d2y by dx2 in terms of y. So from the Taylor series expansion, what do we have? yi plus 1 is equal to yi plus yi dashed, that is the derivative, multiplied by the delta x plus delta x square by 2 factorial into yi double dash. We are taking up to the second order derivative only. Okay. So now, if we consider this term as the error term, this is our error term, right? So yi dash is yi plus 1 minus yi divided by delta x. So this is our forward difference equation, right? Forward difference equation. Similarly, we can write it, the backward difference equation we can also write, which is yi dash equal to yi this is my backward difference equation. And if we just combine the forward and the backward difference equations, we will get the central difference equation, which is more accurate compared to the forward and the backward difference equations. So this is my central difference equation. And using this, we can also write the second order equation, second order derivative, which is yi plus 1 minus 2yi plus I minus 1. We have studied all these things in the numerical differentiation module. So these are the three or four equations which we will be using for our boundary value problems. Okay. Okay. So now let us do one example. Okay. So this is actually, it's very difficult if you have more number of discretization points, if you have more number of points in the domain, your number of equations will increase, and that will increase the size of the matrix. And so we cannot solve it using our normal techniques. So we have to use computer program and solve. So here I will not be solving the entire equation. I will be showing you the steps just. Okay. So, okay. We will see one example. Any doubts up to this?
No doubts.
So suppose we have a equation like this, a non-linear equation we are taking. Y k plus y equals to 0. So d is given to you as 0.07, Rm is given to you as 1. These are the constants which are given to you. And so this is the equation. So first case, we will select the boundary condition with Dirichlet boundary condition. Okay. Dirichlet boundary condition. It is given to you y of 0 is equal to 1 and y of 1 equals to 0.5. Clear? So we will take, here we have 0 and 1, and we'll take 5 intervals. Okay. So we'll have 6 grid points, right? 1, 2, 3, 4. So this is y2, y3, y4, y5, and y1 is given as 0, y6 is 1. So we have to find out y2, y3, y4, y5. So 4 unknowns are there. So we have to basically get 4 equations. So we'll have a 4 cross 4 matrix, then we can easily solve it. Okay, so now we'll rewrite the equation and see. T square y by tx square minus y into rm by km plus y equals to 0. So first we'll substitute the constants. Okay, 0.07 y double dash minus y into rm. Rm is 1, y by y plus 5 equals to 0. So this is my equation. So now y double dash we will substitute this equation, yi plus 1 minus 2yi plus yi minus 1 by delta x. So what is delta x here? So delta x, okay. Delta x is yn plus 1, that is y6 minus y1 by how many intervals? 1, 2, 3, 4, 5. So 1 minus 0 by 5. So it is 0.2. Okay. So delta x is 0.2, remember. So now we will substitute in place of yi plus 1 minus 2yi plus yi minus 1 divided by delta x square, which is 0.2. Let it, this is yi. Is it clear up to this?
Yeah, it's clear.
Clear, right? Okay. So now how many unknowns we have? 4 unknowns, right? y2, y3, y4 and y5. So first we'll have to get 4 equations. So first case we will substitute I equal to 2. Okay. In this equation, if we substitute I equal to 2, it will be 0.07 by this will simplify this constant value. 0.2 square is how much? 0.047 by 4, 41430. Oh, 7. So this is 1.75 into, we'll have, so I equals to 2 we are substituting, right? y3 minus 2y2 plus y1 minus y2 by y2 plus 5 equals to 3. So y1 value we know, right? What is y1? Most probably it is 1. Just 1 minute. So the known quantities will transfer to the other side. So we'll have 1.73y3 minus 3.5 y2 equals to minus 1.75 y2. This is one equation. So like this, again, if we substitute I equal to 3 in this equation, you will get another equation. Again, if you substitute I equal to 4, you will get another equation. Like this, we'll get 4 sets of equation and 4 unknowns we have. We can solve that. Okay. So I'll not do it further. I'll just write the final form of the matrix. You can form a 4 cross 4 matrix and then we can solve it. So if you substitute this, so this will be how much? Y2, right? So first equation is y2 is minus 3.5. Then you have y3 1.75. Then you have 0, 0. Here again you will have 1.75. Then you will have minus 3.5. Then you will have 1.75, 0. 0, 1.75, 3.5, 0, 0, 1.75, minus 3.5. This will be this right hand side term. I'm not writing that y2 by y2 plus 5 minus 1. y3 by y3 plus 5, y4 by y4 plus 5, and this will be y5 by y5 plus 5 minus 3. So this will be my set of equations, and from this we can find out y2, y3, y4, and y5. Using iterative techniques, obviously. You cannot get normal techniques. Is this clear to you, the process?
Yeah, clear. We will solve this through that partial pivoting and back substitution.
Yes, correct.
Okay.
Now here I think this is not a linear equation. So you cannot solve it by the normal techniques because the right hand side terms, this y2 by y2 plus 5, these are all unknown, right? So you don't have, you have to use iterative techniques of non-linear equations. Like we have studied, like I think we studied those techniques, right, in matrix. This back substitution, I think that will not work here most probably. Or you cannot solve it by hand, basically. We have to use this computer programs for solving this non-linear equations, because see, the right hand side is not a known matrix to you. Right hand side is also unknown to you, right?
Yeah.
So
Unknown matrix.
I'll just check it how we can solve it and I'll tell you. So the
Okay.
process is clear. In the exam they will not ask you to solve the whole thing, just 1 or 2 steps they might ask you. Okay, clear, right?
Yeah, clear.
So now we will move to the next topic, which is higher order differential equations. So till now we have looked into how we can solve first order differential equation, second order. We'll see here how we can solve higher order differential equation using numerical techniques, okay, and boundary value problems, obviously. So So x of 0 is given as 1 and dx by dt at t equal to 0 is given as 1. So the order of the differential equation is second order, right? So here first let us assume this y equal to dx by dt. So if y is dx by dt, then the initial condition reduces to y of 0 equal to 0. The second differential equation. Okay, so we can rewrite this equation as dy by dt plus 2 into y cubed plus 1.2x equals to 0. Clear? We have just substituted y in place of dx by dt. The first term is d square x by dt square, right? So it is d by dt of dx by dt. So dx by dt is y. So it is dy by dt basically. Clear?
Yeah, clear.
Okay. Now, first we'll write the slope function. Okay. The initial condition first we'll write, which is given as x of 0. All we'll write in the form of matrix, right? So what is x of 0? It is 1. So x of 0 is 1. What is y of 0? Y is basically dx by dt. So y of 0 is 0. So this is given. Now we need the slope function also. So dx by dt and dy by dt. So what is dx by dt? Dx by dt is simply y. What is dy by dt? Dy by dt means d square x by dt square. So what is d square x by dt square? Or from this equation also we can write dy by dt to minus 2y cube minus 1.2x. So dx by dt is y and dy by dt is minus 2y cubed minus 1.2x. So these two are ready. Okay. Now we'll be using first Euler's method. Okay. So Euler's method if we use, so this is not a boundary value problem. This is an initial value problem because only at one point it is given. At 0 it is given. It is not given at the other boundary. So it is not a boundary value problem. So you should not use finite difference here. We should use our normal Euler's method or the RK method, Hume's method. Clear?
Yeah, clear.
Okay. So let us take our step size to be 0.25. Okay. So we'll do one iteration and we'll see. So, so our slope function is, we'll represent it by f, right? That is our normal convention. So what is f of x0 and y0? What is x0, y0? x0 is 1, y0 is 1. So in this equation, this one, this slope function, here we'll substitute x equal to 1 and y equal to 0. Okay. So y equal to 0 means this is 0 and this is minus 1.2. Clear?
Yeah, clear.
So now we will find out our in the iterative technique x of 0.25 and y of 0.25. So it is basically just Euler's equation was one term. Here we are simultaneously we are using two terms x and y. So it was basically xi plus 1 was x plus h into x dash, right? So here this is our slope. So this will be basically x0, y0 is 1 and 0, h is 0.25, f of x0, f of y0 is 0, minus 1.2. So this will give me x of 0.25, y of 0.25, is equal to, this is 1 and this one is 0 minus 2.25 into 1.2 is minus 0.3. So x of 0.25 is 1. This is what we wanted, right? Value of x. This is not required. So like this, next step if you do, we'll do one more step here. I equals to 2 if you do. So we'll have x of 0.5, y of 0.5, right? So it will be basically x of 0.25, 0.25 h into f of x of 0.25, f of y of 0.25. So this is 1 and minus 0.3 plus 0.25 f of x of 0.25. So f of x of 0.25. So this is my f function, right? So f of x. So it was basically y and minus 2y cube minus 1.2. So this one f. So f of x of 0.25 is 1 and minus 0.3. Y of 0.25 is minus 0.3. So if we substitute this, this is minus 0.3 and this one we have to calculate. 1 second, we'll calculate here. Clear or you're having any problem? Am I going too fast? You can just tell me.
No, no, it's okay.
Okay, fine. Just calculate. We have to calculate this one. What is y? Minus 0.3. Okay. One, two, x is how much? So this comes out to be minus 1.146. So here we'll substitute this minus 0.3 minus 1.14. So if you calculate this one, x of 0.5, y of 0.5, this will come out to be 0.925 and y of 0.5 will be this will be this one, right? Minus this is minus 0.3 plus 0.25 into 1.1430 minus 0.5865. It's 0.925, 0.5865. So this is my after 0.5. Okay, we'll do up to 2 steps here. Clear? How am I doing it? The matrix method for this second order differential equation, how to solve the Euler's equation.
Yeah, I understood.
Okay. So now we'll just do it. The same problem, we'll solve it by RK method. That is Hume's method. We'll try once. So for single variable, what was the thing? It was yi plus 1, yi plus h by 2, k1 plus k2. What was k1? K1 was f of x0, y0, and your k2 was f of x. Sorry. Oh, y of y. So it was f of xi plus h and yi plus hk. So this was for my single variable. So equations will remain same, just we'll have two variables, right? Okay. So first we'll find out what is k1 in this problem. K1 is how much? It is basically f of x0 and y0 for the first step. So my this f function was what? This slope function was y, and this was minus 2y cube minus 1.2x. What was x0? One second. X0 was 1 and y0 was 0. So if you substitute this, k1 you will get as how much? Right. Y0 is 0 and this is minus 1.2. This is my k1. Now k2. K2 is f of x0 plus h for the first step and y0 plus h k1. Right. So what is x0 plus h? X of 0. Okay. One second. X0 plus h. So here x0 plus, one second.
To 1.2.
Not 1.2. X0 is 0 and h is 0.25, right? So it is 0.25, I think. And this y0 plus hk1 will be, this is x0, y0, h is 0.25 and k1 is 0 minus 1.2. x0, y0 is 1 and 0, right? 0. So this is basically 1 and minus. Okay. So here we are taking as 0.5. Okay. What is minus 0.6? So y0 plus hk1 we have, x0 plus hk1 we have. Now we can find out k2. K2 will be equal to f of x0 plus h, y0 plus hk1. So basically this will be f of x0 plus h, and this will be y plus hk1. So this is y minus 2. So how much we got here? This was 1 and minus 0.6, right? So y is minus 0.6 and x is 1. So if you substitute this, 0.6 whole cube minus 0.2. So this is minus 0.6 and minus 0.768. So this is my K2. Now we can find out y of 0.5. Y of 0 plus h by 2, K1 plus K2. So what is y of 0? 0 and 1 and 0, right? So it is basically x of 0.5 and y of 0.5. 1, 0 plus h by 2, 0.25. K1 is 0 minus 1.2 plus minus 0.768. So if you simplify this one, it will come out to be 0.85 and minus 0.49. So here x of 0.5 comes out to be 0.85 using RK2, and we got x of 0.5 as how much? In your Euler we got 0.925. So if you find the true value, you will see that this one is more accurate. The true value we cannot find out here. So this is more accurate. Is the concept clear? The concept is same, just little bit calculation wise it is more computationally expensive.
Yeah, the determinants we are using.
Not determinants, matrix.
Yeah, that matrix we are using.
Hmm. Clear, right? Any doubts, any clarifications, you can ask me.
Yeah, clear up to here. Mm,
Any doubts? From the previous
just
classes, anywhere, any doubts, you can ask.
okay, just a minute. Uh, can you explain that graphical part,
Which one?
the
Today's
beginning of the
class you're
class?
telling?
Yes, the today's class when we have multiple mu values.
Oh, that one. Okay. This one, right? So here what we were
Yeah.
telling is based, if we want to find whether a method is stable or not, any Euler's method or your RK method, anything, whether it is stable or not. So for that we need some criteria, right? How we can declare whether our method is stable or not for any kind of particular differential equation. So for that what we did is we were given this equation was given to us. This yn plus 1 equals to yn minus 1 plus 2h yn dash. Like for Euler's method, we have the equation yn plus 1 equal to yn plus h into yn dash. So like that, some algorithm is given to you. So, and the question it is asked that you have to study its stability. Study means basically you have to give some criteria when it is stable, when it is unstable. So we are applying this to our one simple differential equation dy by dt equals to lambda y. See, if we apply this and do some mathematics, you will get a characteristic equation. This is called the characteristic equation. So one question is obtain this characteristic equation also. So this is my characteristic equation. Okay. Characteristic. So this is the characteristic equation. And based on the characteristic equation, it turned out to be a quadratic equation. So we can solve that equation, right? We'll have two roots, mu1 and mu2. So mu1 is h lambda plus under root 1 plus h square lambda square, and mu2 is h lambda minus under root 1 plus h square lambda square. And the and the solution is of the form c1 mu power n plus 1, mu1 power n plus 1, and c2 mu2 power n plus 1. But we know that the true solution to this differential equation dy by dt equals to lambda y has only one exponential term. However, here when from the characteristic equation if you are coming, you are getting two exponential terms mu1 and mu2, because mu you remember that is already an exponential term, right? So now we are having two exponential terms here. So now one of them has to be a false root, that is one is not correct and the other one is correct. So we have to now find out whether mu1 or mu2 which is the actual solution and which is the false or spurious solution. So how do we do that? So basically from this equation, this equation, say equation A, if I say this equation, in this equation, if one of the mu, say mu2 is much less than mu1, then your only the first term will exist. Second term we can ignore. Similarly, if mu1 is much less than mu2, then also we can ignore the first term, only the second term will exist. So this you have to find out whether your mu1 is greater or mu2 is greater. If they're both almost equal or comparable, there is no much difference, then we can say that this algorithm is not stable for this particular differential equation. So how to do that? For this mu1 and mu2 we plot in terms of these equations we plot h lambda plus 1 plus under root this one and minus. So if you plot this one and you can see one of the terms, which is mu1, it is an exponentially increasing term, whereas mu2 is an exponentially decaying term. So you know that your true solution actually has only exponentially increasing term because the solution is c e power lambda t, right? So that's why your first criteria, first here only it is gone that mu2 cannot be your solution, right? Only mu1 can be your solution. Now, from this equation A, however, mu2 is also present. So if we want to get a stable and a realistic solution, your mu2 term should be very, very small so that we can ignore that term safely. So when is mu2 much, much smaller than mu1? If you see the graph carefully here, on the right hand side of the y-axis, that is for positive x, mu1 is always greater than mu2. That is magnitude I am telling. Magnitude of mu1 is always greater than magnitude of mu2. Whereas on the left side of this y-axis, magnitude of mu2 is always greater than magnitude of mu1. So that means our solution area is the right hand side of this. This is our solution area where mu1 is greater than mu2, not the downside, this part. And when is this mu1 is greater than mu2? Only when h lambda is greater than 0. That is for positive x. So that is our mu1 is greater than mu2 and our algorithm is stable only when h lambda is greater than 0. And when is your h lambda greater than 0? H is a step size and that has always to be greater than 0. That will be always positive. So h is always greater than 0. So basically when your lambda is greater than 0, then your mu1 is greater than mu2. And that is the condition for your stability. So other way around, we can tell that this algorithm will be stable only when this lambda is greater than 0. Is it clear?
Yeah, it is clear. But if suppose the equation we get is cubic or quadratic, if we have 3 or 4 mu values, so we have to check which absolute value is greater, largest. That will be our
Yes,
solution.
yes, yes. Largest
Okay,
means
okay.
there should be considerable difference between the mu1 and the other mu's. Then only it is stable. Otherwise, and this you cannot do in hand. Obviously, you have to write a programming or code for that, and then you have to find it.
Okay, and if they are means nearly equal, means the solution
Then
is
your
not
solution
stable.
is not stable. Yeah, algorithm is not stable. Sorry.
Okay, okay.
Clear, right?
Yeah, yeah, clear, clear. Everything is
Any other
clear.
doubts?
No, 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 no other doubts.
Okay, then when is your exam? When is the exam for this course?
Exam is on 26th October.
26th. Okay, fine. Then 19th
Yeah.
October, we'll have one more session where I'll discuss how to write the MATLAB codes for this and we'll show you how you can visualize it better. 1 hour session I'll take from 7 to 8.
Okay, okay, sure, sure. No issue.
Okay, then fine. We'll meet again. Okay, bye. Thank you.
Okay, okay. Bye. Thank you.